Hello everyone, my name is Kaustubh and today I will be walking you through a package known as Astropy, which is a Python package designed to help astronomers do data analysis. So the entire collection of notebooks that we will be using today is uploaded on my GitHub at a repository called astropy-tutorial. So before we can look at these notebooks, I will spend a few minutes telling you how to acquire these notebooks and how to use them. So the first thing is you need to get hold of this address. So you obviously cannot copy paste from a video, so I will give you about a few seconds to note down. It's not really hard. github.com/vkaustubh/astropy-tutorial. So there are two ways by which you can get hold of these notebooks. The first is the most recommended way, which is to use Git. So Git is a revision control system, and for those of you who are not familiar with it, I highly recommend that you learn the basics of Git. I like to think that the whole software world today runs on Git. If you are a Git user, you obviously have Git installed on your machine. So what you can do is say Git Clone and type out the address. So I'm going to type this out just to tell you that it's not a long address. So I'm going to clone it. So clone is the operation in Git which takes the repository at a particular address and makes a copy of it on your local machine. As you can see, it has finished its job, and if you go to the directory Astropy tutorial and check for the list of files, you now possess all the notebooks that are needed for today's session. If you are not a Git user, don't worry about it. You can open a browser of your choice and you can type the address and you will see this page. Somewhere here you will find the drop down for code, and there is an option which says download zip, and you can easily download the zip file and extract it and then use the notebooks. So these are the two ways by which you can download these notebooks. Now coming to how to use them, so you obviously need Jupyter Notebook or Jupyter Lab in order to use these notebooks. I believe there have been sessions in the past which have explained how to use them. Now on this website, the README file is rendered very nicely, and you can actually see the instructions for downloading and installing the packages that you need. So Astropy is a third-party package. It does not come with Python by default. So you will have to install it unless you are using the Anaconda distribution. If you're using the full Anaconda distribution, Astropy is already present in your Python installation. You don't need to do anything else. But on the other hand, if you are using vanilla Python, you will need to install Python. So this README file has all the instructions you need to install the Astropy package, should that become necessary. I'm going to assume that we are using Anaconda. So by default on my machine, Anaconda is not activated. So being a Linux user, I end up doing something like this in order to activate my Anaconda distribution. But if you are on Windows, you likely have a separate command prompt which is given by Anaconda, and if you are on any other Linux machine, you may have already pre-activated. The thing to watch out for is this base in brackets that is written at the very beginning of the command prompt. If that is present, it means that you are working in the Anaconda environment. This is for Linux users. Windows users will likely not have to struggle so much and will have a straightaway command prompt to use. So let's launch Jupyter Lab by typing Jupyter and Lab as two separate words and pressing enter. This will lead to a new browser window being opened, which will show you all the files on the left. So some of you may prefer Jupyter Notebook, which is perfectly okay, but you must understand that Jupyter Lab is the future. Jupyter Notebook exists because a lot of people use it, but Lab is the next generation version of notebooks. It is far much more powerful, far many more features that once you get used to, you don't want to go back to using a Jupyter Notebook. So I recommend using Jupyter Lab. So at the time of recording this video, there are 5 notebooks here. So let's open the first notebook, which is preparing to dive into Astropy. I'm going to click on this file icon here so that I can hide the file navigator so that the whole screen is occupied by the notebook. I'm also going to go into full screen so that we get rid of the unnecessary address bar at the top. And we are ready. So let's begin. So this notebook doesn't really explain anything about Astropy. It is to give you a preparation into what Astropy is and how to use it, and some basic Python concepts that we are going to need in order to understand Astropy code. So what is Astropy? Astropy is a third-party Python module, which is designed to be like a Swiss Army knife for common programming needs of astronomers. And I like to stress on the word third party, which means that it is not a part of your Python standard library, like when you can easily do import math, import sys, import os, import re, because all these are standard modules in Python, but Astropy needs to be installed. As I've mentioned already, if you are using Anaconda, there is no need to do anything. Astropy is available for you. And in case you're not using Anaconda, you can either use pip install Astropy or conda install Astropy in order to install Astropy. So let's now look at some features of Astropy. There are many features. We have some basic input-output features. So astronomers use something known as FITS files. They interact with a lot of tabular data. They also use something known as virtual observatory in order to search and fetch data. So these are input-output operations. So there are many tools and functionalities available in Astropy to help you with this. We also have basic support for quantities and astronomical coordinates. We have tools for doing some basic statistics and modeling. We have tools for doing cosmological calculations and many more. An important thing to realize is that there is a difference between Astropy, the Python library, and Astropy, the community. So Astropy, when you say Astropy, you can refer to both the Python module and you can also refer to the community. And why that is important is because in the community, there are a whole bunch of other people who have developed many other packages, which are also part of the Astropy community, but not a part of the standard Astropy installation. So these packages are called Astropy affiliated packages. And generally the people who make these packages design them to be compatible with the overall organization of Astropy library. So I've listed a few examples here. We have ccdproc, which is for CCD data processing. We have FOTUtils, which is used for photometric analysis. We have SpecUtils for spectroscopy, AstroQuery, which is a fantastic tool that is used for querying astronomical archives, and many more. And I recommend that you go to this page and check out the total list of packages that are available. You have Astropy HealPix, you have Regions, Reproject, and then you have AGNPy, APLPy, and many more. So just go through these. These are very useful packages to know about, and the link is available in the notebook here. And very important, there is very little to learn as far as Astropy is concerned. So if you're completely new to astronomy, there are some basic concepts that you should be aware of. But everything else is that you do in Astropy is all about having the knack or knowing the art of going through the Astropy documentation, find which submodule or function or class you need in order to do what you want to do. So to that effect, you must definitely check out these 3 links which I have given here. So one is the full user documentation. Oops. Yeah, the page is still loading. Let me come out of full screen mode for a brief moment. So these are some tutorials that are available on Astropy, and you can go, and they address very specific use cases. For example, there is a tutorial on quantities, there's a tutorial on fits files, there's a tutorial on cube, what are called fits cubes. So plenty of tutorials available here which you can take a look at. And then there is an example gallery, so you can see, browse through this and go through the examples. That will also help you understand what Astropy can do. And then we have the full Astropy documentation here, which is like the most comprehensive coverage on Astropy you're ever going to get. So eventually your usage of Astropy will largely be about going through this documentation, finding out what is important for the task that you want to do and use it. For example, you want to do convolution. You would find that there is a section called convolution. There's a sub package called astropy.convolution which you can use. Maybe you want to do statistics, then you can go and look at this documentation and find out more. So to summarize what I've been saying, Astropy, there is very little to learn. That's why I've called this presentation a tour of Astropy, just to give you an idea of what kind of functionality is there. But as such, there's nothing to learn in Astropy. It's all about browsing the documentation and picking the right functions. Now, if you want to successfully use Astropy, it is important to be aware of some basic Python programming concepts. So you need to know your basic syntax, how to do basic input-output, the basic data structures like lists and dictionaries. You need to have some basic ideas of object-oriented programming and basic error catching. Also, behind the scenes, a lot of Astropy packages use data structures provided by other packages. For example, a lot of output that comes from Astropy functions is in the form of NumPy arrays, and therefore it is important that you understand what NumPy arrays are all about. You should also be comfortable with pandas data frames, because a lot of output that comes from the functions in Astropy is in the form of tables, and pandas is a fantastic library for working with tables in the form of data frames. And of course, what's data when you can't plot it? So you should be familiar with plotting libraries to be able to visualize the data. Now, a lot of people don't pay much attention to object-oriented programming. So I have just kept a few minutes of coverage on the basics of object-oriented programming, because you will see a lot of object-oriented approaches being taken in the Astropy library. So the basic idea is the following. Let's say that you have some objects like a Ferrari, a Lamborghini, a McLaren F1. All these are objects. These are unique. They have different colors. They have a different build. Their engine powers are different. But note that while each object here is unique, they also have commonalities. They all have a color. All of them have some color. All of them have a certain build, have a certain engine power. They perform common functions, like there is an interface to change a gear. There is an interface to, pressing the accelerator pedal. There is a pedal for braking and more. So in computer programming, we often come across problems or codes where it is necessary to work with objects which have uniqueness as far as object to object is concerned, but they have a common behavior also. So Computer scientists came up with something known as object-oriented programming in order to write programs that solve problems as a series of objects with some common properties but their own uniqueness interacting with each other. And the most basic construct for object-oriented programming is something known as a class. So what is a class? A class is something that describes the common properties that objects of a given class possess. Right? In this example, the class would describe the common interfaces such as the gas pedal, the brake pedal, the fuel tank, etc. for each car. And once this class is in place, you can create as many objects as you want of that class. So what will change from object to object are the individual properties of the object, like the color, etc. But what will remain common across all the objects are those functions or features that you coded in the class. And believe it or not, you have been using object-oriented programming in Python all along. Yes, so let's look at the simple code which I'm sure by now all of you are familiar with. So here I have declared two strings, s1 equals hello, s2 equals world, and then we have s1.upper which converts the hello into uppercase letters. We can do s2.upper and it gives us world. If I do s1 minus 1, it gives me the last letter of string s1, so that's O. If I do s2 minus 1, it gives me D, which is the last letter of the string s2. Let's look at another series of statements. Here I am declaring dictionaries. So D1 is a dictionary containing keys A and B with values 1 and 2. Similarly, D2 is another dictionary which contains keys C and D and the values true and the list 1, 2, 3. I can do D1.keys, D2.keys in order to recover the keys. I can do D1 bracket the key A in this case to recover the value of the key. So can you connect these simple set of statements with object-oriented programming? Well, it's simple, right? Because when we created these two strings s1 and s2, what we were actually doing is creating two objects of a class known as a string class. Every string was unique. One string contained hello, the other string contained world. The characters were different, the order of characters was different, but they exhibited a common behavior. You could do dot upper on both the strings even though the strings were different. That's because the string class has defined the upper method, and therefore because s1 and s2 both are objects of string class, you can do dot upper and bracket minus 1 and whatnot. Same is the case with dictionaries. Each dictionary is different, but they have common behavior, right? Now, why am I telling you all this? Well, that is because in Astropy utilities, you basically do this a many number of times. You import a class from Astropy and then you create objects of that class. And generally, when I give a demo of Astropy, a lot of people see these statements and are confused. What exactly does this mean? And for this reason, I thought it would be worthwhile spending a little time telling you about the basics of a class and object relationship. For example, you could create a dictionary in the following way. I could say D1 equal to DICT bracket bracket, and then I would say D1 A is hello, D1 B is true. So the way you can interpret this is that dict is a class and you are calling it as if it's a function. Behind the scenes, what it does is call something known as a constructor function, which generates the object D1 for you. And this syntax you will see everywhere. You will see object equal to class. Class is not a function, but it's used as if it's a function. And it has a bunch of properties that we define and we get that object. So for example, if you want to make a fits file, you will create an object of the corresponding class. If you want to define a search routine that will go through an image and detect objects, celestial sources, then we will define the properties of how the search should be conducted and create an object of a particular class. If you want to define a new quantity, we create an object of the quantity class and supply the necessary properties. You want to work with a cosmological model, you will define an object of the cosmology class and so on. So it is for this reason that I thought it would be worthwhile explaining the basics of classes and objects. And that takes us to the end of the first notebook. So we've not even touched Astropy, but I assure you that in the second notebook, we will start looking at Astropy. So let me go to the File tab here and open the second notebook, which is on FITS files, and then hide the File tab again. All right. So what is this FITS? I've been using that word very often. So FITS stands for Flexible Image Transport System. It is a file format, and it was designed by astronomers for astronomers in order to address their data sharing needs. And it is indeed a very flexible image transport system. It's flexible because you can store images which are nothing but two-dimensional arrays. You can store tables which can be both ASCII and binary format. And in a single file, it is possible for us to have both. You can have an image and you can have a table as well. Now that becomes very useful because many a times you have an image and you want to describe the sources in that image and its properties. So in the same file, you can have the image and the table which describes the sources in that image. You can also store multi-dimensional data and more. So a FITS file is made of what are called HDUs. So FITS file is made up of HDUs, and HDU means a header data unit. And as the name implies, a header data unit is made of one header unit, and which is basically metadata, right? Metadata means data that describes data, and this is a compulsory part. And the optional component is the data unit, which contains the actual data. So I think all this will become clear when we look at an example. So let's look at the first example. So firstly, I need to make the FITS module available in Python from Astropy. So the way I do that is say from astropy.io import FITS. So this is basically importing the module. Now in this module, there is a function called open, which accepts a name of the file and returns an object known as the HDU list. Okay, so fits.open data/example.fits, that's the name of the file. The data examples also come with the repository. You don't have to acquire them separately. And what you get is a HDU list. This is a special type of list. It behaves as if it's a list, but it has many other functions also. Now, why should opening a FITS file give you HDU list? Because as I explained, at the most basic level, a FITS file is a collection of HDUs, which means it's a list of HDUs. That's why the way we open a file is HDU list equal to fits.open, name of the file. The convention is to use the variable name as HDU list, but remember that this could easily be X. There would be no problem at all. And if you use the type, you see that it is a special object of the class HDU list. So this is where our object-oriented programming becomes important. You create objects that are of a specific class. So there is a class called HDU list, and HDU list small letters is an object of that type. Now, since this is a list, I can use my list syntax to access a specific HDU from it. So if I say HDU list 0 and say what is its type, it tells me that this is a primary HDU. So primary HDU is a special class that describes the first header in a HDU list. So that's why it's called primary. To get a full summary of a file, you can say print HDU list.info. Info is a method, so it's a function. So you are going to use a pair of parentheses. Now this is a very simple file. So you can see that it has exactly one extension. It's the primary extension, and it has what are called 71 cards and has data of dimension 512, 512 and a format of int16. So this is what info is telling you. It tells you that there is one header data unit in this file, and it's telling you some information about those header data units. So as I said, a header data unit is made of header and data. That's why it's called a HDU. So if you now look at HDU list 0.header and store it in another variable header, the header is a dictionary like object, but what I'll do is we'll print header.cards. So cards basically for historical reasons refers to these pieces of metadata that describe your FITS file. So you can see that when you print header.cards, you get these tuples. Okay, so there's one. So the way you understand these tuples is that the first element is the key, the second is the value, and the third is a comment. This is how FITS headers are structured. FITS headers are a collection of key value pairs with a comment. So this is the key, the value, and the comment. So you can see there are plenty of key value pairs that are present here. Now you will see that at the end there are some empty cards, and you would be like, why are there empty cards here, empty tuples here? Well, that is because the FITS file demands that. FITS file demands that the header be of a specific length, which is why these empty cards are appended at the top to maintain the length of the header. So you can use the headers almost like they are dictionaries. So you see that you can say header bracket n-axis 1 and it prints 512. And if you go back here, you will see that n-axis 1 has a value of 512. And you're using them as if they are dictionaries, right? This is how you would use a dictionary. So that's what's happening here. Header n-axis 1 is 512. If I say n-axis 2, it's 512. If you want to change the header, you do it exactly like you're working with a dictionary. So I'm going to change instrument and change it to my telescope, right? Now you might be wondering, why is instrument written like this? Well, because the FITS file format has another constraint, that the name of an entry in the header should be only 8 characters long, which is why, since instrument is a 9-letter word, they have removed the U to make it 8-letter. So you will find this all over FITS files. The restriction in the FITS format is that the key should be 8 characters long. Great. So we've looked at headers. Now we'll look at data. So if I, just the way I said dot header, in order to get the header, I can say HDU list dot data, 0.data to get the data. And as you can see, this is a NumPy n-dimensional array. So let's make a plot of this. So I'm going to use percentile matplotlib inline so that matplotlib will generate its plots within the notebook. I'm assuming that you have had your share of matplotlib tutoring. So I will not explain the matplotlib commands in detail. So I'm basically importing pyplot and numpy, and then I use imshow. But what I do is, instead of data, I say numpy.log of data. So this is worth emphasizing that data is captured via CCDs. CCDs are linear in nature in their response, but our eyes are logarithmic in nature. So if you want to see an image the way our eyes see them, what you normally do is you take log of the flux values or counts before showing them. So when I say plot.imshow numpy log of data, you will see this beautiful galaxy plotted here. A small exercise for you to play around with. You can, instead of log, you can directly just imshow the data, and you will just get a blank image because our eyes are logarithmics responders. So they will. If you want to see what your eyes can see, then you should take a log. Astronomers often work with something known as Z-scale, which gives a beautiful contrast. Right? Now let's spend a little time here understanding this idea of how images are displayed. So what exactly is imshow doing here? What imshow is doing is that it is measuring your minimum number, that is the lowest value of log of data, highest value of log of data, and it is then using some method of assigning colors to various numbers in between the minimum and the maximum, and that is how this plot is being generated. However, if you want a better contrast, you have to change the way the colors are assigned. And one of the simplest things that you can do to change the contrast of an image is to squeeze a range of values to the same color. So instead of saying I'm going to uniformly allocate colors from minimum to maximum, I will take some chunk in the minimum range and some chunk in the maximum range and give it equal colors, and then take a narrow range between these two and distribute my colors in that. So there is an algorithm to do this. It's called the Z-scale algorithm, and it gives you the limits with which you must plot. So what I'm doing here is importing Z-scale interval, initializing an object of that class. See the pattern I mentioned, object-oriented programming, and then z.getLimits of data will give you z1 and z2. And when I plot my when I do imshow, I say vmin equals z1, vmax equal to z2. So I'm telling the image show function of matplotlib that hey, don't use the minima for and the maxima of the image directly. Use z1 and z2 instead. And now you see it creates a very high contrast version of the FITS file. The image and the FITS header. So feel free to look up on what the Z-scale interval is. It basically involves doing a histogram-like analysis of all the flux values and determining the minimum and maximum which produce a good contrast. So it's very interesting. It's open source, so you can actually download the entire source code of Astropy and actually understand what Z-scale interval is doing here. But long story short, Z-scale interval allows you to compute the minima and maxima in such a way that when you show the image with that minima and maxima, you get a better contrast image. Great. So we have covered how FITS files can be loaded, plotted, etc. Let's now learn how to make your own FITS file. So what I'm doing here is I am importing a submodule of NumPy called random. So I'm saying import numpy.random as nr, and then I am creating a 512 by 512 matrix using using random numbers generated using the normal distribution. Cool. Next, I want to create a FITS file. A FITS file is made up of HDUs, and that collection is known as the HDU list. So I'm creating an object which is of the HDU list class. Then, since I want to add one header, at least in this one header data unit, I create HDU1, which is the primary HDU object. Then I'll assign its data attribute as to this randomly generated data here. So HDU1.data equals data. And then I append this HDU inside this list, right? Now when I want to load the file, I will say write the file, I will say HDU list.write to my file.fits, and the file is created. It's as simple as that. So the steps you follow is you create an object of HDU list class, to which you add objects of HDU types. So there should be at least one which is primary HDU and others which can be some other types. So in fact, I'm going to show this to you in the next piece of code. I want to now append another header to this, which is a table which contains tabular data. So for that, I will first define a column object. So column1 equal to fits.column. I'm giving the column a name. I'm giving it a format. E means that it is a floating point. And I'm saying the array that represents the values of this column is this. So I'm basically generating random numbers between 0 and 1. That's all I'm doing, 10 numbers. And similarly, I'm creating a column 2, and then I'm creating a column definition object, right? And then I'm saying, give me a new HDU, which is called a bin table HDU. So that's a binary table HDU class, and it has a from columns method to which I supply these column definitions. And that's it. I append this and I write my file. So this is a 2 extension or 2 header data unit file that I have created. Now you're going to ask me, this doesn't make any sense. Why are we doing this fits.column, fits.column, fits.calldef, call1, call2? Why am I doing all of this? Now I want you to go back to a point in time where I had mentioned to you that there is nothing to learn in Astropy as such. It's all about finding the right class, reading the documentation and using it. So if you read the documentation on how to make a fits file, it will tell you. If you want to make an image fits file, these are the instructions you must follow. If you want to make a tabular data, these are the instructions you must follow. There is nothing deep to learn here. It is that brilliant programmers have sat down and constructed these classes to represent the objects in as generic manner as possible. And this is how fits files are organized. End of story. There is no why here. It's just there. And that's it. There is nothing deeper to explain here. You might explain something deeper. No, there isn't. Right? So I repeat once again. No deep concept is being covered here. It's just a prescription, a recipe that we are following when we want to do something. That's what Astropy is all about. All right, to wrap it up, that the io.fits library which we imported, there are many other functions available. So we've only seen .open, but suppose you wanted to directly get the header of some file. You could actually say header equal to fits.getHeader and the name of the file. If you wanted to directly read a value, then there is a fits.getVal. If you wanted to directly read the data, then there is fits.getData. And then there is write to, which we have seen. Then we have append, we have update, and so on. So again, no point in me explaining every single function. It's all very well documented. Just go through the documentation. So the expertise you develop in understanding Astropy is directly proportional to your discipline in going through the documentation. That's all, nothing else. So that concludes the tour of the fits file section of Astropy. What we will do now is cover what are called world coordinate systems. So that's the third notebook here. Okay. Cool. So let's cover world coordinate systems now. Suppose you open an image in any image viewer, right? and you move your cursor across the image, you will see that you no doubt get the x comma y value of the cursor, right? Because you're on the 5th pixel on x-axis, 10th pixel on y-axis, so 5 comma 10. But we are working with astronomy, so we would like to know what the RA and dec or some coordinate is at that pixel. How is that possible? How can we, within the FITS file that stores an image, also store the information about how to convert a pixel coordinate x comma y into an actual astronomical coordinate, which is either, let's assume, RA and dec for now, but it could easily be galactic latitude and galactic longitude. The way it is done is that we store some special keywords inside the image header. By now you should be familiar with what a header is. A header is just a collection of key value pairs with some comments. So the header contains a whole bunch of keywords which can be used to convert x comma y into RA comma dec and vice versa. Right? Now, so there are multiple ways by which you can do this. So there is one method of representing which requires, say, only 4 or 6 header keywords. There are other methods which require 20 keywords. The reason so many methods exist is because depending on the situation, each schema or methodology of translating pixels into coordinates has its pros and cons. So if you are looking at a very narrow part of the sky, you can achieve the conversion of x comma y to RA dec using a linear transformation. On the other hand, if your image covers a very big part of the sky, then the curvature of the sky becomes important. So linear transformation will not be enough. You will have to account for second order effects also. So you need more and more header keywords to capture the values of the second order effects. Now most of these operations, reading a header and understanding how the transformation can be done, is handled by Astropy using a submodule called the world called WCS. And whenever you are working with WCS in Astropy, there are 3 simple steps to follow. The first step is get hold of the header. The second is pass it to a Wcs object constructor. And third is use this object for coordinate conversions. That's all. Nothing else. So let's follow that prescription. We are going to import FITS because we need to open a FITS file. Then we are going to import astropy.wcs as WCS, so I don't need to keep on typing astropy.wcs all the time. Let me open a FITS file. Now your masters of FITS file opening now, so fits.open name of the file, and that gives you an HDU list. Now you want to construct a WCS object. The way this is done, if you go back to the prescription I gave earlier, get hold of the header, pass it to a WCS constructor, and then do conversions. So this is what this step captures. So WCS is the module, capital WCS is the class, so WCS.WCS, and the header is accessed by saying HDU list 0.header. And I'm capturing the object created by the WCS constructor in the variable small w. And if I print w, this is what I get as an output. So you see that it has gone through the header. It has detected some relevant values and it has obtained the transformation that is needed. So it says that I am dealing with two axes. The first axis is the right ascension, the second is the declination. The tan basically says that it's using what is known as a tangential projection in order to do the conversions. it has crval and crpix in it. So these two are paired in fact. So crpix says that if at this particular x comma y pixel, that is minus 3929 and 377, the corresponding array dec is 205 blah blah and 47 blah blah. Okay, now you imagine that there is a matrix calculation that happens. So you have a matrix on the right and you do a 2 by 2, so you take a 2 by 2 matrix and you multiply it to a 2 by 1 matrix, you get a 2 by 1 matrix. So these 4 PC1 that you see here, PC11, PC12 are the elements of this matrix transformation, right? So that is the idea. So it's internally, it is basically recovering the elements of a transformation matrix which allows the transformation from x comma y to array comma dec. So most systems basically rely on that. Now since this is a linear coordinate system, we have very limited keywords, but trust me, when we have bigger images or images taken from space telescopes where optical distortion effects can be pretty high, then more complicated keywords can be detected. And now everything after that is simple functionality usage. So this one, so this W object is now a representation of the world coordinate system. What I can do now is invoke a method on it, which is w dot wcs underscore pix to world. So you see it's very straightforward. Pixel to world coordinates. That's what it means. Pix to world. I'm saying 100, 100, 1. Now that deserves a bit of explanation. The first 100 is the x-axis pixel value. So I'm saying, so 100, 100 means that I want to convert the pixel 100, 100 to array and dec. The third comma 1 is very important. You see, when you give me an image, I start counting intuitively from first pixel to last pixel. So first pixel, second pixel, third pixel, and so on. But when I work with NumPy arrays or matrices, then I count from 0, right? So you might be writing some algorithm in which case all the pixel coordinates are counting from 0, for example. Or you may be doing it for personal analysis, in which case you are counting pixels from 1. So the third argument that you see here on the statement highlighted is whether you want to start counting pixels from 1 or 0. So here what I am essentially saying in English is, can you please convert pixel coordinates 100, 100, assuming that I am starting to count from 1 to world coordinates, and that's the output you get. The output says that the 100, 100 pixel as counted from 1 corresponds to an array of 202.69 and a declination of 47.1. As simple as that. You can convert multiple pixels at a time. So let's say that you took all the x coordinates and put them in the first array or list, and in the second argument you give a list of all y coordinates, and it will give you an array of arrays and decs separately. So that you will get one array of only right ascensions, another array of only declinations. So there's a inverse transformation as well. So this is world to pix. So here I am supplying array and dec, and I'm saying give me the x comma y, assuming that I'm counting from 1. That's the way to read this function. So it tells you that, yeah, this corresponds to roughly 100, 100. As you see that I've ignored several digits in the array and dec, so I'm not going to get exact 100, 100, but yeah, we are there. Another useful function is Calc Footprint. So footprint is defined as a collection of array and dex of the four corners of your image. So when you say w.calc footprint, you get an array of 4 pairs. These are array comma dex of the 4 corners of your image. Pretty cool, right? All right, so let's look at some convenience functions now. In this case, these convenience functions actually make the calculations simpler. So remember, WCS is the imported submodule, and I do wcs.utils.pixel to sky coordinate. But remember that this is an independent function. It is not attached to the W object. This is an independent function. So the syntax is slightly different. So I'm saying convert pixel to sky coordinates. Pixels are 100, 100. But remember that wcs.utils.pixel doesn't know what world coordinate system you're using. So I have the third argument in this case has to be the W, to tell that use this W to do the conversions. Now you'll say, but why are you showing me another way of doing this? You already showed me a way of doing it. Well, hold on. I have captured the output. Remember, earlier I was only getting a list of arrays, isn't it? From pixel to world. Here, however, I'm not doing pixel to world coordinate. I'm doing something explicit called pixel to sky coordinate. So if you actually look at output, you see the output is no longer an array. The output is a special object called a sky coordinate object. So when you print output, it tells you that it is a sky coordinate object. It tells you that it is using something known as the FK5 coordinate system. It is telling you that it is working with equinox of 2000. I hope you understand what equinox is, but if not, we can discuss it later. And it's now telling me that array and dec in degrees is this. Okay? So that is one thing. And this, if you want to create your own sky coordinate objects, you can do that using a syntax like this. From astropy.coordinates import sky coord, and c equal to sky coord 10, 20, unit equal to deg, degrees. So you're being very explicit here about your units. Right? Now what I'm going to do is I'm going to show you the power of directly working with sky coordinate objects. Okay? So here what I'm doing in this next code is that I'm importing Astropy, and I'm saying output, which is basically this output of transforming a pixel to sky coordinate object. And I can say output dot transform to, and then I'm passing a class here called astropy.coordinates.galactic. And now when I check, it has given me this new object is basically the same sky coordinates, but in galactic system. So this is a galactic latitude and longitude system that has been used here. So this is the advantage of using this alternate functions, which is pixel to sky coord as opposed to w.pix to world. All right, we are almost to the end of the WCS notebook. So there are many other advantages that you get for using sky coord objects directly. So here is another example. So this time I'm importing sky coord class, and I'm saying distance equal to, so output is already there, right? There is a nice method available in output known as separation. All right. And to the separation, I will supply another sky coord object, which I am calling arraydec of 20247, unit equal to degrees. And now if I print the distance, you see that it gives me the distance between those two coordinates in degrees, minutes and seconds. So in this case, a 28 minutes, 50.1524 seconds distance exists between 20247 and the sky code that was returned from this 100,100 transformation. And output is a special object. You can access its array and deck components individually by saying print output.array and output.deck. So we've successfully navigated the world coordinate system part of Astropy. So that concludes the third of 5 notebooks that I have in store for our tour of Astropy. So let us now move on to the 4th notebook, which is data modeling. All right, let's get ready for this. So modeling is a library in Python, or I wrote that wrong. It is a model in Astropy. It's a library in Astropy, which gives you access to commonly used models for astronomers and also fit them to various data. So as Linus Torvalds says, talk is cheap, show me the code. So let's look at the code. All right. So within Astropy.modeling submodule, there is a sub-module called models, which is basically a collection of classes that are used to represent models. So I'm importing that. Now I'm importing NumPy as NP, matplotlib, and then inline. These are all straightforward stuff. Now I'm defining an X using the linspace function of NumPy. Just to help you jog your memory and recollect, linspace basically accepts 2 arguments, x, x1, x2, and it generates as many linearly evenly spaced points between x1 and x2 as a third argument. So in this case, x is an array which basically is 100 equally spaced numbers between 9 and 14. Now I am initializing a model object. Okay, I am calling it Gauss example 1. Now there are many models available in the models library. I am using Gaussian 1D because that's something we easily work with and recognize. So models.Gaussian 1D, and Gaussian 1D is characterized by 3 parameters. One is the amplitude, which tells you the overall height of the distribution, the mean, which tells you the central location of the peak, and standard deviation, which basically tells you about the spread. So in this case, I have chosen amplitude of 1 and mean of 12 and standard deviation of 0.5. Similarly, I am initializing another object called Gauss example 2, which is also Gaussian 1D, but it is amplitude 2, mean 13.5, standard dev of 0.2. Now here is the interesting part. This is the power of object-oriented programming. Gauss example 1 and Gauss example 2 are 2 objects, but they are governed by a class, and that class supports an addition operation, right? That class supports an addition operation, which is why I'm able to do Gauss example 1 plus Gauss example 2, and internally the definition of the addition that has been done by the programmers here is taking care of defining a new object Gauss total, which behaves indeed like a sum of 2 Gaussians. So very convenient syntax. I'm not sure if you can appreciate it, but this is fantastic programming art that is happening behind the scenes. Now I say Gauss total of x. So I'm using this model object as if it's a function, right? So I'm saying Gauss total of x and store it in y. Now I'll make a scatter plot of x comma y, and this is what it looks like. So you see how convenient your models can be synthesized. Now, if you're not appreciative about Gauss-1D being added together, you can even add a polynomial to it. You can add all kinds of functions together to construct a complicated model, which is what you do in exercises such as spectroscopy, right? You basically are constructing a complex model, which is a combination of several simple models. Okay, what I'll do now is, just to make this data, the synthetically generated data, a bit more realistic, I will add some noise to the data. So the way I do that is I will import that NumPy random module as NR. I will generate some normally distributed random values centered at 0 with a standard deviation of 0.1, and I will say that my Y observation is this. What am I doing here? I'm saying X, which I use to generate Y. I'm saying 0.01 x square plus 12. So that's a polynomial, that's a quadratic polynomial. 12 plus 0.01 x square, that's a polynomial. So let me shade it correctly here. So only this part is just a quadratic polynomial in X. And I'm adding to that my original value of Y, which is basically a mixture of two Gaussians, and some noise that I generated using the above term. Now when I plot this, you see how it has changed. So first of all, you see that it's not that smooth distribution anymore. It has this wiggly nature attached to it that we have associated with it. And you see that there is a quadratic continuum which is now pushing this curve vertically up. So there are two changes that I have made to the data. I have made it noisy, and I have added what I'd call a quadratic continuum, or some kind of an envelope on top of which these Gaussians sit. Now what I want to do is, I want you to pretend that you conducted an astronomical observation, and this is the spectrum, a part of a spectrum that you got. Okay? You conducted an astronomical observation, did spectroscopy, and this is a small part of the spectrum that you have obtained. So I know that we generated this data synthetically. You also know that, but I want you to forget that for a moment, and I want you to pretend that X and Y observed are actual observed empirical data. And the exercise is, can you fit a model to describe this data? And that is what we are going to try and do here. So assume now that this is this. So what do we do? First step is that we must choose a model. Now what model shall we fit? So let us assume that these are spectral features whose wavelengths are known to us approximately. Further, we will assume that each spectral emission line can be described using a Gaussian. Now, what I'll say is, I want to minimize the total number of independent parameters. So what I'll consider is that the difference between these two Gaussians, right? So there's a Gaussian that describes one peak and a Gaussian which describes the second peak. I know that these two correspond to some wavelengths as known from spectroscopy, and even if there is a red shift, blue shift, etc. happening, the distance, the difference in the wavelengths will remain constant. So I want to fit it in such a way that the two Gaussians have a well-known separation associated with them. So, and further, there is an underlying continuum. Okay, we are assuming that the continuum is not varying too fast, and therefore I'll say a quadratic polynomial will be able to describe this. Okay, now you see I'm cheating here a bit. I know how I generated the data, but what I'm trying to tell you here is that the way modeling has to be done by astronomers is that they have to look at the plot and make a judgment, take a judgment call about what model to choose. But I hope it is obvious that even if I hadn't shown you how the data is generated, you would agree that by looking at the plot, all these assumptions are reasonable, that we need two Gaussians that are separated by some distance, sitting on top of a quadratic polynomial that describes this particular trend. So let's see how to do that in Astropy. First, we should construct our model. So it's a Gaussian 1D. I'm choosing some initial values of amplitude, say 1. Mean is 12.1. Standard dev is 0.5. I'm choosing guess values. What you have to appreciate here is that we will be fitting this model, but we need to have some guess values. So these are all guess values. You can, in fact, as an exercise, try to change these values and see how the fitting changes. All right. So I'm now taking a sum of 3 models, 2 Gaussian 1Ds and a polynomial 1D. Now if I say model.parameter names, you see it has given names to the parameters. It has amplitude 0, mean 0, standard dev 0, referring to the first Gaussian. It has amplitude 1, mean 1, standard dev 1, referring to the second Gaussian, and the coefficients of the quadratic polynomial. By the way, we've constructed a model, but our work is not yet complete. We must supply our constraint. Now, here again, don't ask me why am I doing this. This is what is said in the documentation. This is how the library has been designed. So the way a constraint is defined is as follows. We need to define a function. We will call it a constraint on mean. The function is supposed to accept a model. Then I am supposed to calculate using some parameters of that model something, and I am going to return that value. So I'm saying that model.mean underscore 1 minus 1.5. So I'm saying that the separation of means should be 1.5, should be mean 0, and I'm returning mean 0. And in the next step, I will say model.mean underscore 0, and I say dot tide equal to constraint mean. So what I'm saying is, originally tide was not defined, but now I am defining it. And what am I saying? That mean 0 is no longer an independent parameter. It has to be calculated according to the function constraint mean. But what does constraint mean do? It always takes the mean 1, subtract 1.5 and return mean 0. And that is how mean 0 is now tied by the function constraint mean. Now you will say again, no, but why are you writing like this? Again, I repeat, I am merely following a prescription that has been given in the documentation. I am sure the designers of the library would have taken pains to figure out what's the best way to represent constraints, and they came up with this. And this is how you have to use it. Okay, so let's now do the fitting. So within modeling, there is now a library called fitting, and there are many fitting algorithms available, one of which is called the Levenberg-Marquardt least square fitter. So I'm now using that class and creating a fitter object, which is this, right? This is not the right place and time to discuss what a Levenberg-Marquardt LSQ fitter is, but it is one class or one algorithm to determine the best fit parameters for a model given a data. Next is simple. I say model fit equal to fitter. The first argument is the model which I have defined. Second and third are the x and y variables respectively. Once I do that, I can now say model underscore fit dot parameters, and it gives me the list of all the values it has determined. This of course is not easy to read because I don't know what is 0.9, what is 12, what exactly has it calculated. Well, for that you need param names. So the first is the amplitude 0, the second value is mean 0. So let's make it easy, and what I'll do is a little bit of Python trickery, and I will use this thing. I will create a dictionary by zipping param names and parameters. For those of you who may not know, zip basically takes two lists and generates a list of tuples, and then dictionary uses them as key value pairs and creates a dictionary. In your leisure time you can pay more attention to this, but if you really want to call yourself a powerful Python user, you should write statements like this on a daily basis without any problem. So now the scene becomes much clearer. So these are the best fit values that have been determined by the Levenberg-Marquardt fitter to these parameters. Let's now visualize how good the fit is. So what I'm going to do is I'm going to make a scatter plot of x versus y and give them a black color with some transparency. And then I'm going to plot x against the fitted model of x. So these are predictions of the model for every value of x, and I'm going to give them a color of red. And this is what comes out. So you can see it has done a pretty good job of fitting the data. Of course, this whole example is very simplistic. I have cheated in many ways. I knew, for example, what the best model should be. I even knew what good guess values to give to start modeling. But in reality, you have to try out several models. You have to try out different combinations of models, and even for the same combination of models, you have to try out different initial values so that you can determine the best possible fit. And this is just to illustrate Astropy's modeling capabilities. So we are not exactly doing a course on data modeling itself, but I hope you get the general idea how Astropy allows you to model your data. Cool. So we can now head to the fifth and the final notebook for Astropy, which is, I promise you, a very short notebook. It is the shortest notebook out there among all the 5. So the basic idea is the following. You have a cosmological model which is defined as a collection of values, right? Like you have, when you want to define a cosmological model, you say things like omega m, omega lambda, these are all cosmological parameters. And for each assumed set of values, then you have a complicated set of functions that allow you to do things like at what redshift, at a particular redshift, how many arc seconds will be converted to how many kiloparsecs, etc. So the way traditionally you would do it is you would go and open a cosmological calculator online and manually punch in, but that becomes inconvenient when you want to do many calculations in one go. And that is where the cosmology submodule of Astropy becomes useful. So you can import it by just saying from Astropy import cosmology, and when you print this cosmology.parameters.available, it basically tells you some standard set of models that are already present in cosmology module. So there is Planck 18 archive V2 model, there is Planck 15, Planck 13, there is WMAP 9, 7 and 5. These are all survey missions that studied the cosmic microwave background emission and used the data obtained in order to define or measure the cosmological parameters. So you can directly import them by saying from Astropy cosmology import Planck 15, and that's it. You can start using. So this first statement tells you what is the value of the Hubble parameter at redshift 1.5. This tells you what is the density parameter for dark energy in units of critical density for a redshift of 3. This tells you the critical density at redshift 3. This tells you the temperature of the cosmic microwave background at redshift 1000. This tells you what is the angular diameter distance to At redshift 2, this tells you arc seconds per kiloparsec in co-moving coordinate system at redshift 3. This tells you the scale factor of the universe at redshift 4. These are just examples of this. If you actually run this, again, a very nice trick to check what are all the functions available for an object, you can get a very big list here. So you see, I myself don't really recognize most of these. I'm not a great cosmology guy. But you see the number of calculations that are possible using a simple cosmological model. For example, you have distance modulus and so on. And so this is extremely powerful stuff, very, very useful. And that concludes the 5th notebook on Astropy cosmology, as promised, a very short notebook. And it also concludes my tour of the Astropy core library. I hope you managed to get a flavor for the Astropy library, and I repeat once again, conceptually we have not learnt much here. We have just taken a tour of what are the potential capabilities that Astropy offers us, and the real art of using Astropy is all about navigating its extensive documentation, which is on this webpage here, and understanding how to use it. Great. Thank you for your attention. That concludes my tour of Astropy.